Hello. So this is starting our fourth unit, and this is entailing a lot of chapter 4 with one little section from chapter 3, the one we just finished, and section 4.1, short one with a short homework assignment to boot. So we're talking about exponential functions. We're going to evaluate them. We're going to try to look at their graphs and apply some of the just apply some of them. So this is the main parent function of an exponential function. The b value is always positive. So they call this the base. It is always positive and it is not 1. It does not equal 1 because it wouldn't make any sense for the base to be 1 because 1 raised to any real number would just result in 1. So there would be no change in the y value. If b were just 1, this graph would look like a flat line of y equals 1. So it's totally meaningless. So b is never ever 1. If b is greater than 1, then the function is growing. The y values are getting bigger as x gets bigger. If b is under 1, but is still, of course, bigger than 0 because b has to be positive, then the function, the y values are getting smaller as x increases. So that's called a decay. Now, x is here. What could x be? Think about that's domain. You are not dividing by x, nor are you taking the square root of x. X is just the exponents. Can exponents be negative? Yes, they can be negative, they can be 0, they can be positive, they could be irrational, they could be rational. The x is anything. So the x is all real numbers. And so a positive number raised to any real number is going to result in what? A positive number raised to any number is going to result in always a positive number. Always. So the range is greater than 0. So 0 to infinity, not including 0. You cannot start with a positive b value, raise it to something, and get 0. That'll never happen. It'll be a positive number bigger than 0. A little exponent review from Algebra 1, pre-algebra. When you are dividing two powers that have the same base, what do? Well, you subtract them as the shortcut, but the reason why is because x to the sixth, if you expand it, you have 6x's divided by 4x's. A lot of these x's cancel out. 1, 2, 3, 4, and you're left with 2x's in the numerator. And what's in the denominator? 1, because when I say cancel out, I mean dividing factors, and when factors divide, you're left with 1, and x squared divided by 1 is x squared. So from the beginning all the way to the end, we could just skip the middle stuff if we remember that you just subtract the exponents. 6 minus 4 gives you 2. So that's the shortcut. What about when you multiply powers? So x to the sixth times x to the second. Well, x to the sixth is 6x's. X to the second is 2x's. And when you multiply all these, you really have 8x's. So it's really x to the eighth. Well, from the beginning to the end, if you add the exponents, you'll always get the right answer. So x times n times x to the m times x to the n is just x to the n plus n. And some people make a mistake here. Let's say 3 to the third times 3 to the fifth. What does that equal? That does not equal 9 to the anything. It's 3 to the eighth. It equals 3 to the eighth. And some people ask, well, why don't you multiply the threes? And the answer is, you are multiplying the threes. You are. 3 to the third is 3, 3, 3. 3 times 3 times 3. 3 to the fifth is 3 times 3 times 3 times 3 times 3. So all that together is 3 times itself 8 times. So it's 3 to the eighth. Students make a mistake and write 9 to the eighth right here, and they get it wrong. All right, and then this third rule is really just an application of the second rule. Whoops. If you have a power raised to a power, so x to the third to the fifth. Well, what does that to the fifth means? It means you have x to the third 5 times. And x to the third times x to the third, well, each of these is x times x times x. So you're really just reverting to rule 2 here. You just add up all these x's. Well, how many x's do you have? You've got 5 groups of 3, so you have 15. So the shortcut is when you have a power raised to a power, you multiply the exponents. What is x to the 0? That is always 1. X to the 0. Any real number to the 0 is 1. And then x to the negative, a negative exponent, you just reciprocate the base. You flip over this base. You instead of x over 1, you make it 1 over x. And radicals, square root of 6, the cubed root of 6, the fifth root of x to the 4th. What is all that as an exponent? Well, the square root of 6 is 6 to the 1/2. So if you have a calculator and your square root button key is broken, you could just take 6 and raise it to the 0.5, and that is the square root. What about the cubed root? 6 raised to the 1/3. So in general, it is, this is called the index, this number 5, the index of the radical. So that is always in the denominator, and the exponent on the radicand, that's the thing inside, is the numerator of your exponent. So here it is in general form. The mth root of x to the n is the same thing as x to the n over m. All right, let's get back to this. So here's your standard form of exponential function. This will always go through 0, 1, because if you plug in 0 for x, you will get 1. B to the 0 is 1. That's a good thing to remember. And here are the two graphs, the growth and the decay. The blue one is the growth. So as x gets bigger, so does y. That only happens when b is greater than 1. The red one is the decay, and when x gets bigger, the y gets smaller. And that happens when b has to be positive, so b is greater than 0, but it's also less than 1 on the decays. And these exponential functions always have a horizontal asymptote, always. This example has a horizontal asymptote at y equals 0, but I could just add 7 to this, and then the horizontal asymptote would go along with it, and it would be y equals 7 for a horizontal asymptote. Let us evaluate. So what is 2 raised to the 1.99? Go to my calculator. Let's get a new fresh page. And I just take 2 raised to the 1.99, and I get 3.9723. To get more decimals, if you go up, highlight it and press enter, it'll give you a little bit more. So 3.972. 3.972 is 2 raised to the 1.99. What is e to the 5th? E is a number. It is a number. It is between 2 and 3. At one point, you were E years old. And in the Inspire, under this pi button, it has a bunch of what they call transcendental and irrational numbers. And we need E raised to the 5th power. And E is 2. There's a shortcut right there. There's a shortcut right here. E to the x. So E is 2.7. It's a little bit bigger than 2.7. And if you take that number raised to the 5th power, you get 148.413. Now, 1/3 to the -2nd. Notice this doesn't have an approximation sign, because we can do this exactly, and we don't need a calculator, if we remember some exponent rules. That negative flips this base. So this is going to become 3 over 1 to the positive 2nd. And that I can do in my head. 3 to the 2nd power is 9. This also doesn't have a squiggly line. So 25 to the 1/2 is the same thing as the square root of 25. So that's just 5. Notice I didn't say plus or minus 5, because when the square root is presented to you, it's assumed that they want the positive root 99 times out of 100. But if you take the square root, if you have if you're faced with x squared, there's some unknown that equals 25. The only way to proceed here is if you take the square root. Then you have to account for positive and negative, because you don't know x. It could be positive 5 or negative 5. This one, 26 to the 1/2, well, that's the square root of 26. So back to the calculator. The square root of 26, bigger than 5, but not much. 5.099. 5.099. And then this is a funky one, 88.5 raised to the radical 2. Remember, the exponent could be anything. The domain for the exponent is all real numbers. So I'm going to take 88.5 raised to the radical 2, and I get 566.753. 566.723. All right. And these graphs, 2 more slides and we're done here. So let's graph 3 to the x. And I could plug in some random x values. -2 would result in 1/9. So that's an ordered pair, -2, 1/9. -1, 1/3. So when x is -1, you're not much bigger. You're at 1/3. When x is 0, remember, when x is 0, you're at 1 because 3 to the 0 is 1. When x is 1, you're at 3. So 1/3. And when x is 2, you're at 9. 2, 9. So it grows fast, exponentially, some would say. And if you connect all these dots, of course, there are an infinite amount of numbers between 0 and 1. And if you plot all these ordered pairs together, you get this. So notice it has the horizontal asymptote at y equals 0. Notice it goes through the ordered pairs 0, 1. And the domain, well, x can be anything. So the domain is all real. But no matter what x you plug in, even if it's -1,000,000 or 0, or if it's a radical, you will always result in a positive number. So the range is from 0 to infinity. And again, notice the horizontal asymptote at y equals 0. Well, transformations. We know what 3 to the x looks like. What does 3 to the -x look like? What transformation occurs? Remember our transformations? If we replace all the x's with their opposites, then that would be a reflection over the y-axis. So it would just flip over left and right. And that is a reflection over the y-axis. Now, mathematically, I can kind of, let me show you something. Because 3 raised to the -x is the same thing as 3 raised to the -1 times x. But 3 raised to the -1 is, how do I say this? It's the same thing as 3 raised to the -1 and that is being raised to the x. Remember our exponent rules, if you have a power to a power, you multiply. So if you read from right to left, -3 to the -1st raised to the x is the same thing as this, which is the same thing as this. And now this, what's 3 to the -1st power? But it's 1/3. So now we know why that graph looked the way it did, because oh boy. My computer is, there it is. Every time I press left and right, now I need to go one more to the right. Hallelujah. 3 to the -x right here. Notice it now looks like a decay, even though the base is 3, but we have to remember our transformations. I can express 3 to the -x as 1/3 to the x. It's the same thing. So it is actually a decay with a base. The base is between 0 and 1. So it behaves like this. But you can also think of it as a transformation. It's just a flip of this one. All right, what does this do? This -4, 3 raised to the x -4. Well, that minus 4 is next to the x, so we should be thinking it affects the x values, and it most definitely does. It just moves the parent function to the right 4. There is no vertical asymptote. There is no vertical asymptote. If x is, the y values keep on getting bigger, the bigger x gets. There is a horizontal one, though, and this just shifts it to the right 4. Now, these two are in red because these two transformations, the y values are getting affected. This first one, you've got negative 3 to the x. Well, remember, the base cannot be negative, so the base is not negative 3. We need to read this as negative 1 times 3 to the x. And what does that do? It multiplies all the y values by negative 1, which graphically looks like it would flip it upside down. It would flip over the x-axis. Notice the horizontal asymptote, still y equals 0. This one, 3 to the x plus 2, the plus 2 is being added to 3 to the x, which was the original y value. So when you add 2 to all the y values, you are just raising it up 2 units. And so this one actually does change the horizontal asymptote, because when you raise it up 2 units, everything goes up 2, including the horizontal asymptote. So now y equals 2 is the horizontal asymptote, and the range also changed. Now the range is from 2 to infinity, not including 2, though. Finally, if you're given this function, let's say this is a polynomial, not polynomial, but a population function, not polynomial, and it models the population of a country in millions. So first of all, just analyzing this right here, 1.032, this would be the factor in which the population is growing. Notice it's bigger than 1. So as time goes on, the y increases, the population increases. I know that because the base is bigger than 1. And looking at the base, I can think of it as 1 plus 0.032, which in percentages is 100% plus 3.2%. So what this means is, what x is time in years. So year after year after year, the 558 million people are staying. That's 100,000. That's 100% of this population, but then plus 3.2%. So 3.2% more people are coming in year after year after year. 3.2% more people. So we're keeping the original 100% of the population, and we're adding 3.2% of that. So that's why the population is growing. Well, what was the population in 1969? This model begins in 1969. So this is when x is 0. And when x is 0, the base would go to 1. So it's 558 times 1, which is 558 million. In 1991, well, what's the x value now? How far is 1991 from 1969? It is 22 years away. So x will be 22. You go to your calculator, you get this. Remember, it's in millions, so 1,116 million people in 1991. In 2013, what would the x value be? Remember, when x is 0 in 1969. In 2013, it is 44. So notice we're jumping up every 22 years, we're jumping up. So when x is 44, the population is 2,231 million. And 22 years later, which would be 2035, and whoops, I forgot to change that to 66. Population is 4,462 million. Now notice, do you notice a pattern? Every 22 years, look at the population. What's happening to the population every 22 years? What's your guess? It looks like it's doubling. Every 22 years, the population of this country doubles. That's a good thing to know. And if you're doubling, you might think, well, shouldn't the base be 2? And you're right. The base should be 2 if you're doubling, but the base was 1.032. Well, remember, it takes 22 years to double. So if I make this exponent 1 over 22, every time x is 22 or a multiple of 22, I would be multiplying 558 by 2. In other words, I would be doubling it. So notice that 2 raised to the 1 over 22 is 1.032. So that's where, so this number just didn't come out of, this number, if it's hard to see in the beginning for sure, but this number really means doubling, but taking 22 years to double. And that is section 4.1. So you are equipped to do the homework assignment. I think it's very short, 13 or 14 problems.